Continuing our whirlwind tour with very light brush strokes on the transformation of mathematics in the 19th century, we've come to a point where Cantor and others, but especially Cantor, has opened up these huge vistas, very controversial vistas of what numbers are, what sets mean, stuff that really have had a profound effect on the foundations of mathematics. And to go along with that, people realized with the new complexity that was being shown about numbers is that the mathematicians didn't really have a very precise definition of a real number, and it wasn't even realized that you actually needed it. And so Dedekind and others came up with definitions. Cantor was one of them. And the one that's most popular now is due to Dedekind. And the basic idea is that you start from the integers, although really nowadays you start from set theory, which is again something that Cantor initiated. And you start from something at least as simple as the integers. Then you build up the rational numbers, which are just quotients of integers. That's not particularly hard to do. It's very algebraic. Very easy to formalize. And then the leap to from the rationals to the real numbers is quite a subtle one. For example, the cube root of 2 is not a rational number. Is there a way to define it just using notions from the rational numbers and maybe notions of sets? Well, turns out, I'm not going to go into this in any depth in this video, but Dedekind had a brilliant idea. He said, suppose you're looking at the real number line. Say here's a nice copy of the real number line. Suppose right here is the cube root of 2. Then one way to identify what real number you're at is to look at all the numbers that are less than that number. So any real number defines what's called a Dedekind cut, although this is not exactly what he did, but it's pretty close. Just the set of numbers that are less than that number. If you give me a set of numbers that kind of look like a tail starting at some point and going off to the left, you can identify what number they came from by just looking at the right side of the tail. The super clever thing is that you can actually use that to define new numbers that weren't there before. So essentially Dedekind's definition of the cube root of 2 would be take all the rational numbers x. Don't ever mention a real number. Look at all the rational numbers such that the cube root of that the cube of that rational number is less than 2. Now, if we had the ability to cube root both sides of this equation, this would just say x is less than the cube root of 2. It would be all the numbers to the left of the cube root of 2. But notice that this notation over here does not even mention cube roots or anything that's not a rational number. It's just the rational numbers whose cube is less than 2. And what he did was let's define that set of rational numbers to be the real number cube root of 2. It's a very clever thing, and it's a model for a lot of stuff that gets done in 20th century mathematics, defining a new object by a set of old objects, or a structure on old objects. And it takes a really long while to get used to that idea, to be able to really use it. So continuing the story, I'm going to end up about 100 years after the big 1807 event that I started with. And it really is a good place to wrap it up. But the main last thing I want to talk about in the transformation is modern calculus, which now goes under the name of analysis. And the last big figure I really want to focus on is Henri Lebesgue, French mathematician, and many others, but he really is pride of place around 1905, roughly. The task was still unfinished. We still needed to figure out calculus for the very nastiest of the functions you can get with the Fourier method. It still wasn't really clear how it worked. The Riemann integral, the integrals that people like Cauchy and Riemann and Weierstrass, other people like Darboux had invented, they didn't really work very well. There's lots of exceptions and nasty theorems, and it wasn't clear. And Cantor had, as I said in the last video, had come up with these really bizarre sets of real numbers. And the one thing you'd like to think about is, well, can I measure how big those are? Can I, if that's sort of the base of a region in the plane whose height is determined by a function, can I find that area? In other words, can I integrate over these weird sets? It was not working well. And Lebesgue and others revamped the whole theory of integrals. They realized they actually had to re-ground that from the very start and turn it into what's called measure theory. And basically the idea is you need to be able to, whoops, I'm doing something weird here. you need to be able to figure out how big a set of real numbers is, and a pretty arbitrarily weird real set of real numbers. To do Riemann integration, all you need to do is to take an interval of real numbers, say the numbers between 2 and 7, all those numbers, just a chunk of it, and say how big that is. Well, if it's between 2 and 7, the length of that interval is 5. It's not hard. But these kinds of sets, and the sets that come up very naturally when you analyze the weirdest Fourier functions, they're very hard to figure out how big they are. And Lebesgue was the big figure in figuring out how to do that. Now, it turned out that, as in many cases in mathematics, part of the impetus was to deal with exceptional and perhaps kind of borderline pathological cases, or maybe straight out pathological cases. But there were major bonuses for just the theory itself. It very much clarified the relationships of all these concepts, the three crucial concepts of differential or of calculus: integrals, finding the area under a curve; derivatives, finding the slope of a tangent line; and any kind of infinite sum, like the sum of like 1 plus a half plus a quarter plus an eighth. These we knew for many years, since Newton, we knew there were beautiful relations between these, but in the Lebesgue theory, they work so much better. They work for almost incredibly nasty functions, and they work better even for simple functions, even for nice functions that everybody thought they knew how to deal with. Suddenly, oh, it's much easier to prove these theorems we want to be true about the relationship of these concepts. Okay. It's also a major bonus of this new version of calculus. Measure theory turns out to be one of the best foundations for the theory of probability. So here's a little. Let's see if I can zoom in here so you can see this guy. So this is a fun little Venn diagram that I found on the web. Pirate, ninja, and zombie. And so this just wanted to talk a little bit about probability. If you look at probability, let's say this is a sort of a schematic picture of all the things people can be, and maybe the white out here is people who are neither, unfortunately, so boring as to be neither any part pirate, ninja, or zombie. And then here's the blue, which is the pirates, the green is the ninjas, the red is the zombie. Usually with sets, all you care about is, okay, are you in one of these sets? Are you in the intersection of these sets? Are you in the intersection of all three of these sets? Just yes or no questions. But probability asks, how many out of like the 7 billion people in the world, how many are in this set? How many are in this set? How many are in this set? And a good way to have an accurate picture of that is basically just have these sets, the size of these sets, correspond to how many people are in the set, or essentially what's the probability that you're going to end up in the set if you pick a random person. And so, for example, here they say the IRS is the intersection of pirate, ninja, and zombie, which I think is actually rather complementary to the IRS. You can see that that's a smaller set in this picture than, say, the set of all pirates or the set of all zombies. Well, if you're thinking about measuring the size of a set, wait a minute, that's exactly measure theory. That's the insight that Lebesgue and others had, that's the foundation of the theory of integration, is first you need to know how big sets are. And so when you look at the rules for the area of a set, you discover they're exactly the same formal rules for probability of events. And so it became a very beautiful foundation for probability. Still the most common rigorous foundation for probability. Oh, no, not the only one. So here's a great sort of historical fact. Exactly 100 years after the Fourier manuscript, 1907, we have a result that, due to Riesz-Fischer, and there's other people involved, but it definitely is quoted as the Riesz-Fischer theorem. It's a theorem that uses the Lebesgue integral. So it uses this very, very modern approach to calculus. It takes the function space approach. Remember, I was talking about this idea of building up, say, Fourier synthesis out of little pieces and thinking of that as a walk through a space of functions. It uses the geometry of the function space that I was talking about before, this idea of using lengths and angles in this formal space, very seriously, in a very beautiful way. And what it does with those tools is it gets a beautiful, simple theorem about Fourier. It finally says, here's a way to think about Fourier synthesis where all the exceptional cases go away, all the finicky things that people like Dirichlet had to deal with. It all works in a beautiful way if you use the right perspective. And that took a long time. It looked like Fourier was an incredibly useful but finicky tricky theory with lots of hard theorems to prove and lots of special cases you had to check. That's absolutely not true if you use the function space approach and think of it geometrically. And that was something that just was not, people were not able to think that way before around 1900. And then to actually prove that it works, it's crucial that you use this sophisticated version of calculus, the Lebesgue integral. So this really wraps up the story in a beautiful way. In a way, this talk has all been about this 100-year period between Fourier's manuscript and the Riesz-Fischer theorem, and a story that takes something that was really hard to understand rigorously but clearly useful and turn it into something that actually mathematicians understood and it's just one of the most beautiful things ever once you get it in the right way. Just a little bit more about the profound changes that the Fourier story led to. It really introduced true rigor into mathematics. As I said, calculus was a huge part of mathematics, and it was really not rigorous. And people mostly didn't worry about that and didn't even realize how unrigorous it was, to be honest. It vastly generalized the scope of calculus to new functions, new ideas, new levels of generality and abstraction. It opened up new notions of infinity, of number. What is a number? Well, how do you even define a real number? That kind of thing. Or are there other numbers out there you can define in interesting ways? Sets, it let us know that sets were interesting things and could be a foundation of mathematics. It led to a new and reasonably firm foundation for mathematics, namely set theory, and very allied with very careful use of logic. Now, one of the things that really was impossible to do without this firm foundation is the work of Kurt Gödel, who in the 1930s showed that there actually were very, very deep unexpected complexities. That when you look at this phrase, foundation for math, it's inescapably super tricky and complicated. But nobody would have ever discovered that without first getting it as firm a foundation as possible. So that really comes out of this story as well. It gradually showed the power of abstraction. That's another change that I haven't focused on too much, although this idea of moving from the analysis of a single function to the analysis of a space of functions and how they relate to each other geometrically, that's one of the biggest things where it moves up a level in abstraction. And between say 1900 and 1950, that was the next big thing. So between 1807 and 1907, it was really a change in the level of rigor of mathematics in a way. And then between 1907 and 1950, the abstraction then takes off. The rigor has been more or less taken care of, although Gödel threw a wrench into that. But then people realized, oh wow, we've got a taste of this new abstract way of doing things, and it really took off. That's for another talk, really. But it does definitely say that much of mathematics, especially by 1950, it would have been extremely hard to explain to these incredibly smart people like Lagrange and Gauss, just because the level of abstraction was so much higher. But it really is necessary. It's not just for its own sake. Many applications of mathematics are okay without the modern approach. As I said, most calculus students, and so let's say most working engineers, you learn a version of mathematics, and even the Fourier story, that isn't radically different from the 1807 version. But many applications do require this new understanding of mathematics. And even if the end users don't necessarily use the rigorous version or the abstract version, it wouldn't have been developed without that rigor and that abstraction. So to me, it's a beautiful story how this one idea was such an important catalyst for such profound changes in mathematics. I want to give a shout out to, I realize I just never wrote it down in here. Let me give a shout out to a particular person, David Brassoud. I got a lot of the core of this talk from a couple of books, A Radical Introduction, I think it's called A Radical Introduction to Real Analysis, and A Radical Introduction, I don't have them in front of me, so I might be getting the title a little bit wrong, not Radical, A Radical Introduction to Lebesgue Integration. Very much taking, and these are real textbooks that go into the details, maybe more details than I would even want, but they were definitely very interesting reads to see how transformative these ideas were. Okay, I think that's where I'm gonna stop this series. Thanks.